Deep in the constellation Atlas, 47 light-years from Earth's patient orbit, 3 planets move through space in a gravitational ballet that should not exist. They circle their young star in perfect resonance for every 2 orbits the innermost world completes. The middle planet completes exactly 3, while the outermost world traces a single, stately revolution. This mathematical precision emerges from chaos theory's predictions like a whispered impossibility, each world pulling and tugging at its companions in ways that create stability from what should be destruction. The resonance holds with a precision that makes atomic clocks seem sloppy. Over millions of years, not a single orbital period has drifted by more than a few minutes. This clockwork perfection puzzles astronomers because resonant chains typically form through slow, careful migration planets gradually spiraling inward through their star's protoplanetary disk, their orbits naturally falling into mathematical harmony. But 3I Atlas accomplished this feat in mere hundreds of thousands of years, around a star barely old enough to have cleared the dust from its stellar nursery. The star itself burns with the fury of youth, its surface temperatures fluctuating by hundreds of degrees as stellar storms rage across photospheric plains larger than Jupiter's great red spot. Magnetic field lines twist and snap, launching coronal mass ejections that would strip away the atmospheres of any normal planetary system. Yet the 3 worlds of 3I Atlas maintain their atmospheric envelopes as if protected by some invisible shield, their orbital dance continuing undisturbed through magnetic tempests that should have rendered them airless, lifeless rocks billions of years ago. Each planet maintains an orbital eccentricity so low that their paths around the star trace nearly perfect circles. This geometric precision defies the gravitational chaos that typically characterizes young planetary systems, where worlds migrate, collide, and scatter like billiard balls struck by an angry god. The inner planet completes its orbit in 4.2 Earth days, its surface temperature locked in perpetual twilight as tidal forces have synchronized its rotation with its revolution. The middle world takes 6.3 days to circle the star, while the outer planet requires 12, 6 days each period, a perfect mathematical multiple of the others. Computer simulations run backwards through time cannot reproduce the system's formation. Every model that creates the observed resonance also predicts collisions, ejections, or orbital decay that never occurred. The gravitational interactions between 3 massive worlds in such close proximity should produce chaotic dynamics, with orbital periods gradually shifting until the resonance breaks and the system falls apart. Instead, 3I Atlas demonstrates a stability that extends millions of years into the past and, according to dynamical models, millions more into the future. The mystery deepens when astronomers examine the system's angular momentum distribution. In our solar system, the Sun contains 99.8% of the system's mass, but only 0.5% of its angular momentum. Most of the rotational energy resides in the orbital motion of the planets, particularly Jupiter. This distribution tells the story of planetary formation, migration, and gravitational interactions spanning billions of years. But 3I Atlas shows an angular momentum distribution that matches no theoretical model, as if the planets and star formed from fundamentally different processes than anything observed elsewhere in the galaxy. The star's rotation period of 7 hours creates magnetic field geometries that should tidally lock the inner planet while destabilizing the orbits of the outer worlds. Instead, the inner planet spins once every 4.2 days, exactly matching its orbital period in perfect synchronous rotation. While the middle and outer planets maintain rotation rates that correlate with no known tidal theory, the gravitational tides that should gradually slow planetary spins and expand orbits appear to operate under different physical laws in the 3I Atlas system. Transit observations reveal planetary sizes and masses that place all three worlds in the category astronomers call super-Earths, too large to be terrestrial, too small to be gas giants, with densities that suggest compositions intermediate between rock and ice. These measurements carry uncertainties that would normally provide comfortable margins for theoretical interpretation. But every possible composition model for planets of these sizes and masses requires formation scenarios that contradict the system's observed youth and orbital architecture. The planets maintain their impossible dance with the patience of geological time, each world precisely where it should not be, moving exactly as it should not move. Radio telescopes detect faint emissions from the system at frequencies that suggest complex electromagnetic interactions between the planetary magnetospheres and their star's variable magnetic field. These signals pulse with periodicities that match neither the planetary orbital periods nor the stellar rotation, hinting at electromagnetic processes that current plasma physics cannot fully explain. Only took a few hundred millennia to make a mockery of our best theories about planetary formation timescales. Only required 3 small worlds to challenge fundamental assumptions about gravitational dynamics. Only needed perfect orbital resonance to whisper that the universe operates by rules more subtle and strange than human mathematics has yet discovered. Sometimes, the universe whispers its secrets in frequencies we have not yet learned to hear. The 3i Atlas system continues its ancient dance, each orbit a quiet revolution against the comfortable certainties of planetary science, each transit across the star's face a gentle reminder that cosmic truth often wears the patient mask of impossibility. The star at the heart of the 3i Atlas system burns with an adolescent fury that should have already written the obituary of any planetary companions. At barely 2 million years old, an infant by stellar standards, it radiates energy across the electromagnetic spectrum with the unpredictable violence of youth. Its surface churns with magnetic storms that dwarf anything our own sun produces, launching coronal mass ejections with energies equivalent to billions of hydrogen bombs detonating every second. Stellar flares erupt from its photosphere with temperatures exceeding 20 million Kelvin, creating brief moments when the star outshines itself by factors of 10 or more. Yet around this stellar tempest, 3 worlds formed and achieved orbital stability in a time frame that challenges every model of planetary accretion. Current theory suggests that terrestrial planets require 10 to 100 million years to assemble from the slow gravitational accumulation of planetesimals, rocky debris left over from stellar formation. The process begins with microscopic dust grains sticking together through electrostatic forces, gradually building into pebbles, then boulders, then kilometer-sized bodies that eventually collide and merge into planetary embryos. In the 3i Atlas system, this entire sequence must have occurred while the star was still contracting from its initial gravitational collapse, its luminosity varying by orders of magnitude as it settled into stable hydrogen fusion. The protoplanetary disk of gas and dust that gave birth to these worlds would have been bombarded by stellar winds powerful enough to strip away volatile materials and scatter small particles into interstellar space. Somehow, despite this cosmic sandblasting, solid matter accumulated into planetary cores and retained enough mass to gravitationally capture substantial atmospheres. The rapid formation timeline becomes even more puzzling when astronomers consider the isotopic ratios detected in the planetary atmospheres. Spectroscopic analysis reveals abundances of heavy elements that typically require multiple generations of stellar nucleosynthesis to produce. These isotopes should not exist in such concentrations around such a young star, unless the planets formed from materials that had traveled vast distances through the galaxy before settling into the 3i Atlas system. The chemical signatures suggest a cosmic migration story that spans hundreds of millions of years. Yet the planets themselves show no signs of the atmospheric erosion that should accompany such ancient wandering. The central star's variable luminosity creates a habitable zone that shifts inward and outward like a cosmic tide, sometimes encompassing all three planets, sometimes none. During stellar maximum, when magnetic reconnection events trigger massive flares, the star's energy output increases by factors of 3 to 5, pushing the habitable zone far beyond the outermost planet's orbit. During quiet periods, the reduced stellar radiation allows ice to form on all three worlds simultaneously. This cyclical heating and cooling should create atmospheric instabilities that destroy weather patterns and prevent the establishment of stable climate systems. Instead, each planet maintains atmospheric conditions that appear remarkably constant over timescales of thousands of years. The inner world shows no signs of atmospheric stripping, despite receiving stellar radiation doses that would boil away Earth's oceans in mere centuries. The middle planet maintains cloud patterns that persist through multiple stellar activity cycles, while the outer world exhibits seasonal variations that correlate with its orbital position rather than the star's unpredictable energy output. The star's youth means that its rotation rate and magnetic field strength continue to evolve on timescales of millennia rather than millions of years. Young stars typically spin faster and generate stronger magnetic fields than their mature counterparts, creating electromagnetic environments that vary dramatically over short periods. The 3I Atlas star shows rotational periods that have decreased by nearly 10% over the past 1,000 years of observations, yet the planetary orbits show no corresponding changes in their resonant relationships. This temporal disconnect suggests that the gravitational interactions between the planets create a dynamical system more stable than the star-planet interactions that typically dominate young planetary systems. The three worlds appear to have achieved a state of collective equilibrium that insulates them from the chaos of their stellar environment, like a gravitational choir that continues singing in perfect harmony despite the discordant solo of their temperamental conductor. Stellar evolution models predict that the 3I Atlas star will continue brightening and stabilizing over the next 50 million years as it settles into main sequence hydrogen burning. During this period, most young stellar systems lose their initial planetary companions to gravitational scattering, atmospheric erosion, or tidal disruption. The fact that three massive planets survived the violent birth throes of their star suggests either extraordinary luck or physical processes that current astrophysics does not fully understand. The mystery deepens when astronomers examine the star's chemical composition. Stellar spectroscopy reveals abundances of lithium, beryllium, and other light elements that should have been destroyed by nuclear reactions during the star's pre-main sequence contraction. These elements serve as cosmic chronometers, their presence indicating stellar ages much younger than the apparently mature planetary system they illuminate. The chemical clock of the star disagrees with the dynamical clock of the planets by factors of 10 or more. Only took 2 million years to assemble what should require 50 million. Only needed perfect timing to coordinate planetary formation with stellar evolution in ways that defy statistical probability. Only required a young star to nurture mature worlds, while simultaneously trying to destroy them with adolescent rage. The star continues its violent youth while its planetary children dance their ancient dance. Each solar flare, a reminder that cosmic nurseries operate by rules more complex than human theories have yet imagined. In the gentle mathematics of orbital resonance, three worlds find stability around a star too young to permit their existence, too chaotic to allow their survival, too alien for our current models to explain. The innermost world of the 3I Atlas system possesses a density that places it in the theoretical no man's land between rocky terrestrial planets and gaseous mini-Neptunes. At 1.7 times Earth's radius and 3.2 times Earth's mass, It should classify clearly as either a super-Earth with a substantial rocky core or a sub-Neptune with a thick hydrogen-helium envelope. Instead, its bulk density of 4. 1 grams per cubic centimeter suggests a composition that exists nowhere else in the known universe, too dense for a gas-dominated world, too light for a purely rocky planet. This density anomaly represents more than a simple measurement uncertainty. Repeated observations using multiple techniques, transit photometry, radial velocity measurements, and gravitational microlensing all converge on the same impossible value. The planet contains mass equivalent to 3 Earths compressed into a volume that should accommodate only 2.5 Earths worth of rock and metal. The missing volume cannot be explained by atmospheric compression, core mantle differentiation, or any known planetary structure model. Theoretical compositions that might produce such densities require exotic states of matter, typically found only in the cores of white dwarf stars or the crusts of neutron stars. At the pressures and temperatures expected in a planet of this size, normal rock and metal cannot achieve the required compression. Some models propose cores composed of metallic hydrogen or degenerate matter. But these phases require pressures millions of times greater than anything possible in planetary interiors. The density suggests physics beyond the standard model of condensed matter. The planet's gravitational field exhibits subtle anomalies that compound the mystery of its internal structure. Precise tracking of spacecraft trajectories during hypothetical flybys, calculated from the observed orbital perturbations of its companion worlds, reveals gravitational moments that indicate mass distributions fundamentally different from terrestrial planets. The gravitational signature suggests a core that occupies nearly 80% of the planet's radius, surrounded by a mantle so thin it challenges the basic mechanics of planetary differentiation. On Earth, the iron-nickel core comprises roughly 30% of the planet's radius, with the remaining volume occupied by silicate mantle and a thin crustal shell. This structure arose from billions of years of gravitational settling, with dense metals sinking toward the center while lighter rocks floated upward. The 3I Atlas inner planet appears to have inverted this process, concentrating nearly all its mass in a central region while maintaining a low-density outer shell that should have collapsed under its own gravity eons ago. The planet's surface shows no signs of the geological activity that should accompany such an unusual internal structure. Thermal infrared observations detect surface temperatures that vary smoothly with stellar illumination, indicating efficient heat distribution through atmospheric circulation. There are no hotspots, volcanic emissions, or tectonic signatures that would mark the release of gravitational potential energy from ongoing core contraction or mantle convection. The world appears geologically dead despite possessing an internal structure that should generate enormous amounts of heat. Atmospheric spectroscopy reveals a chemical composition dominated by water vapor, carbon dioxide, and methane molecules that should exist only as ices at the planet's distance from its star. The atmospheric pressure exceeds 10 Earth atmospheres, yet the observed molecular absorption lines suggest temperatures and densities that cannot coexist under normal thermodynamic conditions. The atmosphere behaves as if governed by an equation of state that differs subtly but fundamentally from terrestrial physics. The planet's magnetic field strength, inferred from radio emissions and interaction with stellar wind, indicates a magnetosphere comparable to Jupiter's, despite the world's much smaller size and presumably solid composition. Magnetic field generation typically requires convection in a liquid metallic core, but the inferred core composition and structure should not permit the fluid motions necessary for dynamo action. The magnetic field exists without an apparent mechanism for its generation, persisting at strengths that should decay in mere thousands of years without continuous regeneration. Transit observations reveal atmospheric features that change on timescales of hours rather than the days or weeks typical of planetary weather systems. Cloud formations appear and disappear with periodicities that match neither the planet's rotation period nor its orbital motion around the star. These rapid atmospheric dynamics suggest energy sources beyond solar heating and tidal flexing, perhaps gravitational interactions with its companion worlds or electromagnetic coupling with the stellar magnetic field. The planet's rotation period remains precisely synchronized with its orbital period, maintaining perfect tidal locking despite gravitational perturbations from its companion worlds that should gradually decouple rotation from revolution. This synchronous state requires continuous fine-tuning of the planet's rotational energy, yet no mechanism exists for the necessary energy dissipation or redistribution. The planet spins at exactly the right rate to keep one face perpetually pointed toward its star, as if cosmic forces conspired to preserve this geometric perfection. Stellar occultation measurements during planetary transits reveal atmospheric layers with refractive indices that change abruptly at specific altitudes, creating optical effects that suggest discrete changes in atmospheric composition or phase. These layered structures resemble the stratospheric boundaries found in gas giant atmospheres, but they appear in a world whose mass and size should preclude such complex atmospheric architecture. The observations hint at atmospheric physics operating under conditions that current models cannot reproduce. Only took 3 Earth masses to challenge everything we know about planetary interiors. Only needed perfect tidal locking to raise questions about rotational dynamics that have guided celestial mechanics for centuries. Only required one impossible density to suggest that matter behaves differently in the alien environment of the 3I Atlas system. The innermost world continues its rapid orbit. Each revolution a quiet demonstration that planets can exist in states that transcend the comfortable categories of terrestrial and gaseous, rocky and volatile, possible and impossible. High above the surface of the middle planet, clouds of vaporized iron drift through an atmosphere that should not exist. Spectroscopic analysis reveals absorption lines characteristic of gaseous metals, iron, magnesium, silicon, and aluminum suspended in atmospheric layers where temperatures barely exceed 800 Kelvin. At such relatively cool conditions, these elements should condense into solid particles and rain down to the surface within hours or days. Instead, they maintain their gaseous state for months at a time, forming persistent cloud formations that stretch across hemispheres and persist through multiple orbital cycles. The metallic vapors exhibit circulation patterns that defy conventional atmospheric dynamics. Instead of following the pressure gradients and temperature differences that drive weather systems on terrestrial worlds, the metal clouds move in spiral formations that correlate with the planet's magnetic field lines. Iron vapor streams flow along invisible magnetic highways, creating atmospheric rivers of vaporized metal that span thousands of kilometers while maintaining coherent structure for weeks at a time. These magnetic weather patterns suggest atmospheric processes that operate more like plasma physics than meteorology. Earth's atmosphere contains trace amounts of metallic vapors, sodium from meteor ablation, iron from cosmic dust, but these constituents comprise less than 1 part per billion of the total atmospheric mass. The 3I Atlas middle planet maintains metal vapor concentrations that exceed Earth's levels by factors of millions, creating an atmosphere where gaseous metals contribute significantly to atmospheric pressure, opacity, and thermal properties. The sheer abundance of vaporized metals implies surface processes that continuously replenish atmospheric metallic content against gravitational settling and chemical condensation. The source of these metallic vapors remains a profound mystery. Volcanic outgassing typically produces water vapor, carbon dioxide, and sulfur compounds, but rarely generates significant quantities of vaporized metals. Impact events from asteroid or comet collisions can briefly inject metallic vapors into planetary atmospheres, but such transient phenomena cannot sustain the observed concentrations over geological timescales. The planet shows no signs of ongoing volcanic activity, recent impact cratering, or surface processes capable of vaporizing metals at the observed rates. Some theoretical models propose that intense stellar radiation could heat surface rocks to temperatures sufficient for metal sublimation, but the 3I Atlas middle planet receives only modest stellar flux comparable to Mars's solar heating. The required surface temperatures would demand greenhouse heating mechanisms that far exceed the warming potential of conventional atmospheric gases. Alternative proposals invoke exotic heating sources, radioactive decay from unusually heavy isotopes, tidal heating from gravitational interactions with companion planets, or electromagnetic heating from coupling with stellar magnetic fields. The metallic clouds exhibit optical properties that create atmospheric phenomena unknown in terrestrial meteorology. Iron vapor clouds scatter visible light with wavelength dependencies that produce spectacular atmospheric displays, sunsets that shift through the entire visible spectrum as different metals absorb and re-emit photons at characteristic frequencies. Magnesium clouds create silvery reflective layers that act like atmospheric mirrors, while aluminum vapors generate iridescent formations that shimmer with colors that have no names in human language. Atmospheric circulation models struggle to explain how gaseous metals remain suspended against gravitational settling. Metal atoms are typically dozens of times more massive than the hydrogen, helium, and molecular gases that dominate planetary atmospheres. Conventional atmospheric dynamics predict that such heavy constituents should settle toward the surface within planetary rotation periods, creating stratified atmospheric layers with metals concentrated in dense, low-altitude clouds. Instead, the metallic vapors maintain nearly uniform distributions throughout the observable atmosphere. The magnetic field interactions that guide metal vapor circulation require electromagnetic coupling strengths that exceed theoretical predictions by orders of magnitude. Gaseous metals in planetary atmospheres typically exhibit weak responses to magnetic fields because thermal motion randomizes particle velocities and prevents coherent electromagnetic behavior. The organized, field-aligned flows observed in the 3I Atlas system suggest that the metallic vapors behave more like magnetized plasma than ordinary atmospheric gas, despite temperatures and pressures that should preclude plasma formation. Spectroscopic monitoring reveals that the metallic cloud compositions change with planetary orbital position, as if the atmosphere responds to varying stellar radiation or gravitational influences from companion worlds. During closest approach to the star, iron and magnesium concentrations increase, while aluminum and silicon levels decrease. Near orbital aphelion, the trend reverses, creating seasonal variations in atmospheric metal content that follow no known pattern of stellar heating or gravitational perturbation. The planet's atmospheric mass exceeds theoretical predictions for worlds of its size and stellar distance by factors of 3 to 5. Standard models of atmospheric retention predict that planets in the 3I Atlas system should have lost most of their gaseous envelopes to stellar wind stripping and thermal escape within the first few million years of their existence. The persistent, metal-rich atmosphere suggests either continuous atmospheric replenishment from unknown sources or atmospheric retention mechanisms that operate beyond the scope of current planetary science. Radio observations detect electromagnetic emissions from the planet at frequencies characteristic of cyclotron radiation, the telltale signature of charged particles spiraling along magnetic field lines. The emission pattern suggests that some fraction of the atmospheric metals exists in ionized form, creating a tenuous ionosphere composed of metallic plasma rather than the hydrogen and helium ions found in terrestrial upper atmospheres. This metallic plasma layer could provide the electromagnetic coupling necessary to organize atmospheric circulation along magnetic field lines. Only took vaporized metals to rewrite atmospheric science textbooks. Only needed impossible weather patterns to suggest that planets can sustain atmospheric processes that terrestrial physics cannot explain. Only required persistent metal clouds to whisper that the universe operates atmospheric systems beyond the comfortable boundaries of earthly meteorology. The middle planet continues its stately orbit, metallic clouds streaming through its alien atmosphere like rivers of light. Each spectroscopic observation a gentle reminder that cosmic weather systems follow rules more subtle and strange than human theories have yet discovered. Radio telescopes across Earth detect a symphony of electromagnetic signals emanating from the 3I Atlas system, not the random static of cosmic background radiation, but organized pulses that repeat with mathematical precision while following no pattern that human physics can decode. The signals arrive at frequencies ranging from 30 MHz to 3 GHz, covering the same radio spectrum used for terrestrial communications. Yet their structure suggests sources and mechanisms that operate by entirely different principles than any known astrophysical phenomenon. The radio emissions pulse with periodicities that correlate weakly with the planetary orbital periods, but never quite match them exactly. The strongest signals repeat every 23 Earth days close to the inner planet's 4.2-day orbit, but offset by precisely 43 minutes in a pattern that remains constant across years of observation. Secondary emission peaks occur every 6.31 and 12.64 days, again approaching but never exactly matching the middle and outer planet's orbital periods. These slight discrepancies suggest that the radio sources move independently of the planets themselves, perhaps linked to atmospheric or magnetospheric phenomena that drift slowly relative to planetary motion. Each planet in the system generates its own distinct radio signature, but the individual emissions interact and interfere with each other in ways that create complex beating patterns and harmonic resonances. When the planets align in their orbital dance, their combined radio output sometimes amplifies to intensities that exceed the sum of individual contributions by factors of 10 or more. During other orbital configurations, the signals partially cancel each other, creating radio quiet periods that last for days before the electromagnetic chorus resumes its alien song. The magnetic field interactions that generate these radio emissions defy conventional plasma physics models. On Jupiter, similar radio signals arise from charged particles accelerating along magnetic field lines, creating cyclotron radiation as electrons and ions spiral through the planet's magnetosphere. But the 3I Atlas signals exhibit polarization characteristics and frequency distributions that suggest particle acceleration mechanisms operating at energies and magnetic field strengths impossible for planets of the observed sizes and masses. Detailed analysis of the radio spectrum reveals fine structure that hints at electromagnetic processes more complex than simple synchrotron or cyclotron radiation. The signals contain frequency modulations that repeat on timescales of minutes to hours, creating what radio astronomers describe as electromagnetic chirps, rapid frequency sweeps that rise and fall in pitch like cosmic bird songs. These chirping patterns occur simultaneously across widely separated frequency bands, suggesting coherent emission processes that coordinate electromagnetic activity across vast ranges of the radio spectrum. The magnetic field configurations necessary to produce such organized radio emissions require planetary magnetospheres with geometries that current dynamo theory cannot explain. Standard models predict that planets generate magnetic fields through convection in liquid metallic cores, creating dipolar field structures similar to bar magnets with north and south poles. The three-way atlas radio signatures suggest magnetic field topologies that include quadrupolar, octupolar, and higher-order components, complex field geometries that typically arise only in rapidly rotating stars or exotic astrophysical objects. Computer simulations that attempt to reproduce the observed radio patterns require magnetic field strengths exceeding those of Jupiter by factors of hundreds to thousands. Such intense magnetic fields would demand planetary cores composed entirely of superconducting materials or exotic matter states that remain stable under planetary interior conditions. The energy requirements for maintaining these electromagnetic fields exceed the total gravitational binding energy of the planets themselves. Yet the radio emissions continue year after year with no signs of weakening or decay. The radio signals exhibit properties that suggest they propagate through interplanetary space by mechanisms more efficient than ordinary electromagnetic radiation. Signals from the outer planet reach Earth with intensities that require impossible transmission efficiencies, as if the radio waves experience amplification rather than attenuation during their journey through the interstellar medium. Some theoretical models propose that the 3I Atlas system generates coherent radio emission through maser or laser-like processes, creating electromagnetic beams that maintain their intensity across interstellar distances. Polarization measurements reveal that the radio waves possess circular and linear polarization characteristics that rotate and evolve during propagation in ways that suggest interaction with structured magnetic fields extending far beyond the planetary orbits. The polarization signatures indicate that the entire 3I Atlas system sits within a large-scale magnetic environment, perhaps a cosmic magnetic bubble that confines and organizes electromagnetic activity across scales ranging from planetary magnetospheres to interstellar space. The temporal evolution of the radio emissions suggests that the electromagnetic environment of the 3I Atlas system changes on timescales that correlate with no known astrophysical processes, over periods of months to years. The signal intensities and frequency distributions drift gradually in patterns that repeat with periodicities of decades. These long-term variations might reflect slow changes in planetary magnetic fields, orbital dynamics, or interactions with the stellar magnetic environment. But the observed time scales match no theoretical predictions for planetary electromagnetic evolution. Attempts to decode the radio signals using pattern recognition algorithms and information theory techniques reveal statistical structures that resemble organized communication more than random astrophysical noise. The signals contain embedded periodicities, frequency correlations, and amplitude modulations that exhibit complexity measures comparable to human language or music. While these patterns likely arise from natural electromagnetic processes rather than artificial intelligence, their organized structure suggests physical phenomena that operate by principles more subtle than current electromagnetic theory encompasses. Only took impossible magnetic fields to challenge fundamental assumptions about planetary dynamo processes. Only needed radio emissions that follow no known pattern to suggest that electromagnetic phenomena in the 3I Atlas system operate by rules beyond terrestrial physics. Only required a broken symphony of cosmic signals to whisper that the universe generates electromagnetic music in frequencies and harmonies that human science has yet to understand. The radio signals continue their alien broadcast. Each pulse and chirp a gentle reminder that cosmic magnetic fields can create electromagnetic phenomena that transcend the comfortable boundaries of plasma physics and planetary magnetism. The orbital paths traced by the three worlds of 3I Atlas carve through space with mathematical precision that violates the NICE model. The theoretical framework that successfully explains the architecture of our own solar system and hundreds of other planetary systems discovered across the galaxy. According to this model, planets form at various distances from their star and then migrate inward or outward through gravitational interactions with leftover planetesimals and gas disk material. The final orbital configuration reflects billions of years of chaotic evolution, with planets scattered, ejected, or settled into stable resonances through slow dynamical processes. The 3I Atlas system shows no evidence of this expected migration history. The planets occupy orbits that appear to have been carved from the vacuum of space with geometric precision, their paths forming perfect ellipses with eccentricities so low they approach the mathematical ideal of circles. The inner planet's orbit deviates from circularity by less than 0.073, a precision that exceeds the measurement accuracy of most astronomical instruments. The middle and outer planets maintain similarly perfect orbital geometries, their paths through space displaying the mathematical regularity of a cosmic clockwork, rather than the scarred trajectories of worlds shaped by billions of years of gravitational chaos. The spacing between planetary orbits follows no known relationship from planetary formation theory. In our solar system, orbital distances roughly follow Titius-Bode relationships, mathematical progressions that reflect the physics of disk accretion and resonant interactions during planetary assembly. The 3I Atlas orbital architecture exhibits spacing patterns that match no theoretical model, with planetary distances that appear chosen to optimize gravitational stability rather than arising from natural formation processes. Each planet maintains orbital inclinations within 0.1 degrees of perfect coplanarity, all three worlds circling their star in the same geometric plane with precision that suggests coordinated evolution rather than independent formation. In typical planetary systems, gravitational interactions and collisional events during formation create orbital inclinations that scatter planets across ranges of several degrees. The 3I Atlas planets move as if guided by invisible tracks that preserve their orbital alignment despite millions of years of gravitational perturbations from their massive companions. The gravitational interactions between the three worlds create what dynamicists call a Laplace resonance, a specific type of orbital harmony where the innermost planet completes exactly 4 orbits for every 2 orbits of the middle planet and every 1 orbit of the outer planet. This 4-to-1 resonance represents one of the most stable possible configurations for a 3-planet system, yet it typically requires millions of years of careful orbital migration to achieve. The 3I Atlas system displays this perfect resonance despite forming around a star barely old enough to have completed its initial gravitational contraction. Computer simulations that attempt to recreate the observed orbital architecture consistently fail to produce stable 3-planet resonances within the required time frame. Models that begin with realistic initial conditions, randomly distributed planetary embryos in a protoplanetary disk, evolve into chaotic configurations with planetary collisions, ejections, or orbital decay. Simulations that artificially impose the observed final state demonstrate that the resonant configuration should remain stable for billions of years, but no known physical process can establish such perfect orbital harmony in mere millions of years. The orbital periods themselves exhibit temporal stability that exceeds theoretical expectations for such a young system. Precise timing of planetary transits across the stellar disk reveals that orbital periods remain constant to within nanosecond precision over observational baseline spanning decades. This temporal regularity suggests that the planets experience no measurable orbital decay from tidal interactions, atmospheric drag, or gravitational wave emission processes that should gradually spiral the worlds inward toward their star over astronomical timescales. Gravitational perturbation analysis reveals that the 3 planets exchange angular momentum and orbital energy through their mutual interactions in ways that perfectly conserve the system's total dynamical properties. When the inner planet's orbit expands slightly due to tidal forces, the outer planets automatically adjust their motion to compensate, maintaining the overall resonant structure with precision that suggests active feedback mechanisms rather than passive gravitational dynamics. The system behaves as if equipped with a cosmic gyroscope that automatically corrects any deviation from perfect orbital harmony. The absence of observable planetary migration conflicts with direct evidence from the system's debris disk structure. Infrared observations reveal dusty rings and gaps at specific distances from the star that typically mark the gravitational influence zones of migrating planets. These disk features indicate that substantial planetary migration should have occurred. Yet the current orbital configuration shows no signs of the expected migration history. The disk remembers planetary motions that the planets themselves appear never to have experienced. Long-term orbital integration calculations demonstrate that the 3I Atlas configuration represents a profound minimum in the system's gravitational potential energy, a state of maximum stability that would naturally arise if the planets could somehow adjust their orbits to optimize collective gravitational harmony. However, no known mechanism allows planets to actively minimize their potential energy through coordinated orbital changes. The observed configuration suggests that the planet somehow chose the most stable possible orbital arrangement from among countless alternatives. The orbital elements' semi-major axes, eccentricities, inclinations, and resonant angles exhibit correlations that match no statistical distribution expected from chaotic planetary formation processes. The mathematical relationships between orbital parameters appear too perfectly organized to arise from random gravitational evolution, yet too precisely structured to result from any known deterministic process. The orbits suggest underlying order that transcends both chaos and predictability. Only took perfect orbital resonance to challenge decades of planetary migration theory. Only needed mathematical precision to suggest that gravitational dynamics in the 3I Atlas system operate by principles more subtle than Newtonian mechanics predicts. Only required 3 impossible orbits to whisper that cosmic clockwork can achieve precision that exceeds the chaos of normal planetary evolution. The 3 worlds continue their eternal dance, each orbit a gentle revolution against the comfortable assumptions of planetary dynamics. Each perfect alignment, a quiet demonstration that gravitational harmony can emerge from processes that human celestial mechanics has yet to discover. Across the surfaces of all 3 worlds in the 3I Atlas system, heat flows in patterns that mock every principle of planetary thermodynamics. The inner planet, locked in perpetual tidal embrace with its star, should display extreme temperature contrasts between its day and night hemispheres, the sunward face baked to incandescent fury while the shadow side freezes in absolute darkness. Instead, infrared observations reveal temperature variations of less than 50 Kelvin across the entire planetary surface, as if some invisible mechanism redistributes thermal energy with impossible efficiency. The temperature uniformity cannot be explained by atmospheric circulation alone. Even Venus, with its crushing carbon dioxide atmosphere and runaway greenhouse effect, maintains temperature differences of several hundred degrees between equatorial and polar regions. The 3I Atlas inner planet achieves thermal equilibrium across hemispheres that receive stellar radiation differing by infinite ratios, the day side basking in perpetual noon, while the night side experiences eternal midnight. The required heat transport would demand atmospheric winds exceeding the speed of sound, yet spectroscopic observations detect no evidence of such violent weather systems. The middle planet exhibits thermal anomalies that challenge fundamental assumptions about radiative energy balance. Its surface temperature remains constant at 340 Kelvin, warm enough to maintain liquid water despite receiving stellar radiation that should heat it to barely 280 Kelvin. The excess thermal energy amounts to 40% more than the planet receives from stellar heating, suggesting internal heat sources that exceed the gravitational energy release from planetary formation and radioactive decay combined. The planet glows with its own thermal radiation like a miniature star, yet shows no signs of the geological activity that should accompany such enormous internal energy generation. The outermost world presents perhaps the most puzzling thermal signature of all. Despite its distance from the central star, where stellar heating should maintain surface temperatures below 200 Kelvin, infrared observations detect thermal emissions corresponding to a global average temperature of 290 Kelvin, nearly as warm as Earth's surface. The planet receives less than 5% of Earth's solar flux, yet maintains surface conditions that could support liquid water oceans under appropriate atmospheric conditions. The required internal heat source exceeds the planet's total gravitational binding energy, suggesting thermal processes that operate beyond the scope of conventional planetary physics. Thermal infrared mapping reveals that all three planets exhibit heat distribution patterns that correlate with no known geological or atmospheric process. Rather than the random patchwork of hot and cold regions expected from volcanism, impact heating, or atmospheric circulation. The thermal maps display organized patterns that repeat with periodicities matching the orbital resonances between the planets. Hotspots appear and disappear in synchronized cycles, as if the planetary heat sources respond to gravitational tidal forces or electromagnetic coupling between the worlds. The synchronized thermal variations suggest that the planets exchange energy through mechanisms that operate faster than thermal conduction or atmospheric transport. When the inner planet's temperature increases during particular orbital configurations, the middle and outer planets simultaneously experience corresponding thermal changes, despite the vast distances separating them and the multi-day light travel times that should delay any electromagnetic communication. The thermal coupling operates instantaneously across astronomical distances, implying energy transfer processes that transcend the speed of light limitations of conventional physics. Spectroscopic analysis of the thermal emissions reveals blackbody spectra that deviate subtly but consistently from the Planck distribution expected for objects at the observed temperatures. The deviations appear in specific wavelength bands that correspond to vibrational and rotational energy levels of common atmospheric molecules. But the intensity ratios suggest population distributions that violate thermal equilibrium assumptions. The planetary surfaces appear to emit thermal radiation as if matter exists in excited quantum states that should decay within microseconds under normal conditions. The thermal anomalies become even more mysterious when compared with theoretical models of planetary cooling. Standard calculations predict that planets of the observed sizes and compositions should have completed their initial thermal contraction within the first 10 million years after formation, settling into steady states where internal heat generation balances thermal radiation to space. The 3I Atlas planets continue generating excess thermal energy after tens of millions of years, as if powered by energy sources that operate independently of gravitational potential energy and radioactive decay. Some theoretical models propose exotic heating mechanisms to explain the thermal signatures, gravitational wave interactions, dark matter annihilation, or coupling with quantum vacuum fluctuations. However, the required energy densities exceed observational limits from other astrophysical phenomena by orders of magnitude. Alternative proposals invoke modifications to thermodynamic laws under extreme gravitational or electromagnetic conditions, but the 3I Atlas system shows no evidence of the exotic space-time curvature or field strengths that would permit such departures from established physics. The thermal emission spectra exhibit time-variable components that suggest the heating mechanisms respond to external influences on timescales ranging from hours to years. During certain orbital configurations, The thermal output from all three planets increases simultaneously, while other alignments produce coordinated decreases in planetary temperatures. These variations follow no pattern predicted by tidal heating, stellar irradiation changes, or electromagnetic induction from the variable stellar magnetic field. Long-term monitoring reveals that the planetary thermal emissions exhibit slow secular changes that correlate with no known astrophysical process. Over decades of observation, the excess thermal energy from each planet has increased by several %, suggesting that whatever mechanisms power these worlds grow stronger with time rather than weaker. Conventional heat sources should decay exponentially as gravitational contraction slows and radioactive isotopes undergo nuclear decay. Yet the 3I Atlas thermal anomalies intensify with the patience of geological time. The atmospheric greenhouse effects on all three planets operate with efficiencies that exceed theoretical maxima for known greenhouse gases. Even under the most extreme assumptions about atmospheric composition and pressure, conventional greenhouse warming cannot account for the observed surface temperatures. The atmospheres trap and redistribute thermal energy with nearly perfect efficiency, suggesting radiative transfer processes that violate detailed balance requirements and approach thermodynamic impossibilities. Only took impossible heat distribution to rewrite planetary thermodynamics textbooks. Only needed thermal coupling across astronomical distances to suggest that energy transport in the 3I Atlas system operates by mechanisms faster than light and more efficient than conduction. Only required synchronized temperature variations to whisper that cosmic thermal processes can achieve coordination that transcends the comfortable boundaries of heat transfer theory. The three worlds continue radiating their excess thermal energy into the cosmic void. Each infrared photon, a gentle reminder that planetary heat engines can operate by principles more subtle and strange than human thermodynamics has yet discovered. The isotopic signatures detected in the atmospheres and surface materials of the 3I Atlas planets tell a story that contradicts everything astronomers know about stellar nucleosynthesis and galactic chemical evolution. Spectroscopic analysis reveals abundances of heavy elements, particularly iron-60, aluminum-26, and calcium-41 that should not exist in detectable quantities around such a young star. These radioisotopes possess half-lives ranging from hundreds of thousands to millions of years, meaning they decay to undetectable levels within relatively short cosmic timescales. Their presence in the 3I Atlas system suggests recent exposure to nucleosynthetic processes that typically occur only in the cores of massive stars or during supernova explosions. The iron-60 concentrations exceed galactic background levels by factors of thousands. This isotope forms exclusively in the silicon-burning shells of stars more massive than 20 solar masses, and gets dispersed into the interstellar medium only when these massive stars explode as supernovae. The half-life of iron-60, approximately 2.6 million years, means that detectable quantities can persist only if produced within the very recent past on astronomical timescales. The 3I Atlas system shows iron-60 abundances that would require supernova detonations within 10 light-years of the system within the past few million years. However, no evidence exists for recent supernova activity in the stellar neighborhood surrounding 3I Atlas. The local interstellar medium shows no signs of supernova shockwaves, neutron star remnants, or the characteristic X-ray emissions that mark recent stellar explosions. The system appears to sit in a quiet region of the galaxy, far from the star-forming regions and massive stellar associations where supernovae typically occur. The isotopic evidence demands nearby supernova activity that left no other observable traces in the surrounding cosmic environment. The aluminum-26 signatures present an even deeper mystery. This isotope forms in the hydrogen-burning shells of massive stars and gets ejected during stellar winds and supernova explosions, but it also gets produced in smaller quantities during nova explosions and cosmic ray interactions with interstellar dust. The 3I Atlas planets show aluminum-26 abundances that require continuous production and incorporation over millions of years, as if the system experienced repeated exposure to multiple nucleosynthetic sources throughout its formation history. The calcium-41 detections violate fundamental assumptions about cosmic ray interactions and galactic chemical evolution. This isotope forms primarily through cosmic ray spallation, high-energy particles, smashing into heavier nuclei and fragmenting them into lighter elements. The production rates depend on cosmic ray fluxes and target material compositions in ways that astronomers understand with considerable precision. The observed calcium-41 abundances in the 3I Atlas system exceed theoretical production rates by factors of hundreds, suggesting cosmic ray environments more intense than anything observed elsewhere in the galaxy. Carbon isotope ratios provide additional evidence for anomalous nucleosynthetic histories. The ratio of carbon-12 to carbon-13 in planetary atmospheres differs significantly from solar system values, indicating formation from materials that experienced different stellar processing environments. The carbon signatures suggest that the planetary building blocks formed in regions of the galaxy with stellar populations, metallicities, and nucleosynthetic yields fundamentally different from our solar neighborhood. Yet stellar population synthesis models predict uniform isotopic compositions across galactic regions with similar ages and metallicities. Oxygen isotope anomalies compound the mystery of the system's chemical evolution. The 3-isotope plot of oxygen-16, oxygen-17, and oxygen-18 ratios reveals compositions that fall along mass-dependent fractionation lines, characteristic of high-temperature processing in stellar environments. These signatures typically arise from gas phase chemistry in stellar atmospheres or supernova shock fronts, yet they appear in solid planetary materials that formed at the relatively low temperatures of protoplanetary disk conditions. The isotopic evidence suggests that solid matter in the 3I Atlas system retains memory of high-energy processes that occurred before planetary accretion. The rare Earth element patterns detected through high-resolution spectroscopy exhibit abundant signatures that match no known stellar nucleosynthetic process. Elements like europium,